Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we'll continue our learning on Prosper software. And today's topic is about simulation or modeling for a dewatering well for a CBM reservoir. All right, CBM is coal bed methane. So usually to produce gas from CBM, we perform the dewatering, okay, using, for example, ESP, electrical submersible pump. So now we will model a well, a dewatering well with ESP to dewater the CBM reservoir. Okay, and of course, we will perform the modeling and simulation using Prosper software. Okay, so you can follow me. We start with this step. Okay, fluid description, fluid, oil, and water. Okay, method black oil, separator single stage separator, emulsion no, PVT warnings, disable warning, water viscosity, use default correlation, viscosity model, Newtonian fluid, and for the well, flow type, tubing flow, well type, this one, we open the drop-down menu, CBM producer. Okay, so in Prosper, we will deal differently between producer in a conventional reservoir and for CBM. Okay, and for the artificial lift, open the drop-down menu. You can see if we select CBM producer, then automatically the Prosper will give us for the artificial lift method only ESP or PCP, electrical submersible pump or progressive cavity pump. Okay, so in this case, we will use ESP, electrical submersible pump. And for the type, model produced oil only. Okay, but we can also have model produce oil and gas in annulus. In this case, we select this one. You can also type in the user information and also the comments here. And then for the calculation type, predict, I prefer on land, onshore for the CBM production for this modeling, of course. And for the model rough approximation, range full system, brine properties default, type case hole, nose and control, inflow type single branch. Okay, we click done and we will wait. Okay, so the Prosper is now ready to input this one, the PVT section. Okay, so you can see the PVT input data section is much simpler for CBM. All right, and you can see there is no matching tab here. Okay, and now you can follow my data, gas gravity 0.6. Okay, and then for the water salinity 100,000 ppm, gas liquid ratio 0. Okay, mole percent of H2S, CO2, and nitrogen 0. Okay, click done. Now we go to the next step for the IPR. Okay, so for the reservoir model, we go to this one, CBM producer. Right, CBM producer. And now you can see now we have gas liquid ratio. Actually, we will use 10 here. So the actual gas liquid ratio is 10. Okay. Reservoir pressure 800. Reservoir temperature 100. So the information of gas liquid ratio that will be used is this one, 10 SCF per STB. Reservoir model, productivity index 2, stock tank barrel per day per PSI. And now in this case, we need to input the relative permeability. Okay. Residual water saturation 0.2, residual gas saturation, for example, 0, water endpoint relative permeability 0.8, gas endpoint relative permeability 0.8, Corey exponent for water 1.5, for the gas it is 2. The relative permeability water reduces when Sg higher than 0, not Sg higher than the residual gas saturation. We select no perm. Okay. And then from here, we can click calculate. You can see the absolute open flow, the maximum flow rate is 1,222.49 stock tank barrel per day. And you can plot the result. I want to show only the rate and pressure. Rate on the x-axis, the horizontal axis, and pressure on the vertical axis, the y-axis. Click done. Okay, so now you can see we have a straight line IPR. Okay, because the dominant flow, the dominant fluid will be water. Okay, and the gas is very small, only 10 SCF per STB. All right, click done, click done. Okay, so this is the IPR, and now we need to input the information here for the equipment data section. I will edit the data for deviation survey, downhole equipment, geothermal gradient, and average heat capacities. Click done. I click edit, I mean. For deviation survey, 0, 0. It is a vertical well, quite short, 2,600. Create the plot. You see, vertical well, finish. Click done. Now the well, the downhole equipment, Christmas tree at 0, 0 depth. Then we will have tubing down to 2,500 with inside diameter of 2.875, tubing inside roughness of 0.0006 inches with outside diameter of the tubing 3.25, the same roughness, and the casing inside diameter 6.1, the same roughness. We assume it, rate multiplier 1. And lastly, we have casing down to the bottom of the well at 2,600. Casing inside diameter 6.1, the same roughness, the same rate multiplier. Click done. Okay, and then we need to input the geothermal gradient. The overall heat transfer coefficient is 8. You can follow me, 60 at 0 depth, and at the reservoir depth, the temperature is 100 feet. Click done. Yeah, this is the default numbers for average heat capacities for oil, gas, and water. No need to edit it. Click done. Check the summary. Drawdown hole. Okay, so this is the schematic of our well, but later on we will install ESP at this well. Click done, done, done. We need to wait. Okay, so this is the schematic of our well without ESP, but now we will install ESP to our well. Usually we perform design and we do the design by inputting the data here. The calculation will be done here. But let's assume I skip that. Okay, let's assume that I already know the design, the proper design of my ESP to this well. So I can skip this one, cancel. If you're interested in ESP design, you can check my video on my other videos in this channel, or maybe later on in the future, we can create more videos about ESP. Okay, but in this video, I will just concentrate on the modeling of the well, and I just straight on input the ESP, install the ESP to my well. Okay, and here we open this section.